Welcome to the deep dive. Today we're tackling some pretty complex physics,
Oh, yeah.
diving into the world of supersymmetry
I like it.
and grand unification.
All right.
You've provided a mix of research papers and lecture transcripts,
Okay.
so we'll synthesize those to give you the most important takeaways.
Sounds good.
Okay, let's start with a basic question.
Okay.
The standard model of particle physics has been incredibly successful.
It has been, yes.
So why are physicists even looking for something beyond it?
That's a great question, and it's one that drives a lot of research in particle physics.
Yeah.
While the standard model has been fantastic at explaining many of the particles and forces we observe, it leaves some pretty big mysteries unsolved.
So it's like having a puzzle with a few missing pieces.
Exactly. And some of these missing pieces point to something deeper,
Right.
something beyond the standard model.
Okay.
One of the most glaring gaps is something called the hierarchy problem.
Okay.
It's all about the huge difference between the electroweak scale, where the electromagnetic and weak forces become unified, and the Planck scale, where gravity becomes significant.
I see. So it's a problem of scales.
Yes.
Can you give me an idea of just how big this difference is?
It's truly mind-boggling.
Okay.
Imagine an ant and the entire Earth.
Wow.
That's roughly the difference between the electroweak scale and the Planck scale.
Wow. That puts it into perspective. And the standard model doesn't explain why there's such a huge discrepancy.
Not at all. And that's a problem because it suggests that something fundamental is missing from our understanding of how the universe works.
That's where supersymmetry comes in.
Right.
Okay.
Supersymmetry, or SUY,
Right.
is a theory that attempts to bridge this gap
Okay.
and address other limitations of the standard model by introducing a whole new set of particles,
Oh?
a superpartner for each known particle.
Okay. So it's like doubling the number of particles in the universe. Why would that help?
Yeah.
Does it just make things more complicated?
It might seem that way at first,
Right.
but it actually brings a beautiful symmetry to the particle world.
Okay.
You see, there are two fundamental types of particles. Fermions, which make up matter,
Right.
and bosons, which carry forces.
Okay.
SUSY proposes a fundamental link between these two,
Okay.
suggesting that they're not as different as they seem.
So SUSY says that for every fermion, there's a corresponding boson and vice versa.
Precisely.
Interesting.
And this new symmetry has profound consequences.
Okay.
For example,
Yeah.
it can help stabilize the Higgs boson mass,
Okay.
which is closely tied to the electroweak scale.
Can you explain how that works?
In the standard model, the Higgs boson mass is extremely sensitive to quantum fluctuations. It's like trying to balance a pencil on its tip.
Right.
Any tiny disturbance can make it topple over.
And these quantum fluctuations would push the Higgs mass up to the Planck scale.
Right.
Okay.
Which would make the electroweak scale incredibly unnatural.
Right.
But in supersymmetry, the superpartners come to the rescue. Their contributions to the Higgs mass act like a counterweight,
I see.
stabilizing the pencil and keeping the electroweak scale where we observe it.
So it's like a cosmic balancing act. The
Exactly.
superpartners help keep the Higgs mass in check.
Exactly.
Gotcha.
This stabilization mechanism is one of the most compelling reasons to believe in supersymmetry.
Okay.
And it's not just about the Higgs boson. SUSY has the potential to solve other mysteries as well,
Right.
like the nature of dark matter and the tiny masses of neutrinos.
Intriguing.
You mentioned that your research paper dives into the details of SUSY using something called two-component spinor notation.
Yes, it does.
That sounds pretty intimidating.
It does sound pretty intimidating.
It might sound complex,
Right.
but it's just a different way of describing particles with spin.
Okay.
Think of it like using different lenses to look at the same object.
Right.
Sometimes a particular lens just gives you a clearer view.
So it's like a mathematical tool that makes describing supersymmetry easier.
Exactly. The standard way of describing spin uses four-component spinors,
Right.
which are essentially mathematical objects with four components. But for supersymmetry, it turns out that using two-component spinors is much more convenient.
Why is that? What makes two-component spinors better suited for SUSY?
It has to do with the nature of the superpartners.
Okay.
Remember, for each known particle, SUSY predicts a superpartner with a different spin.
Right.
Using two-component spinors makes it much easier to describe how these superpartners transform under Lorentz transformations.
Lorentz transformations. Remind me what those are.
They're essentially transformations that describe how physical quantities change when viewed from different reference frames, especially frames moving relative to one another.
Right.
Think about looking at a moving car from the side of the road versus from another car also traveling down the road.
So two-component spinors provide a clearer picture of how these superpartners look from different perspectives depending on their motion.
Precisely. And because SUSY relates particles with different spins,
Right.
it's crucial to have a mathematical framework that handles these spin transformations gracefully.
Oh.
Two-component spinors do just that.
I'm starting to see why physicists might prefer this notation.
Right.
It sounds like it reveals a deeper connection between the mathematical description and the underlying physics of supersymmetry.
That's exactly right.
Okay.
And it's just the beginning of our exploration of SUSY.
Okay.
The paper also gets into the heart of the theory,
Okay.
exploring the supersymmetry algebra,
Okay.
which defines the relationships between the different SUSY generators.
Generators. What do those do?
Think of generators as the mathematical building blocks of symmetries.
Okay.
In the case of CSY,
Yeah.
these generators describe the transformations that relate particles to their superpartners.
So the supersymmetry algebra is like a set of rules that govern how these transformations work.
Precisely.
Okay.
And it's through understanding this algebra that we can really grasp the power and beauty of supersymmetry.
This is all fascinating.
Yeah.
But I have a feeling we're just scratching the surface here.
You're right about that. The world of supersymmetry is vast and full of surprises.
Right.
And it gets even more interesting when we connect it to the idea of grand unification,
Okay.
which is where Susskind's lectures come in.
Grand unification. That sounds epic.
It is.
What's that all about?
Grand unification, or GUT for short,
Okay.
is the idea that the three fundamental forces of the standard model, the strong force,
Oh, yeah.
the weak force,
Right.
and the electromagnetic force are actually different aspects of a single unified force at very high energies.
So it's like a cosmic melting pot where all the forces become one.
Exactly.
All
And
right.
it's not just the forces that unify.
Okay.
GUTs also suggest that the different types of particles in the standard model,
Yeah.
including quarks and leptons,
Right.
are all part of a single grand unified family.
Wow. That really changes the picture, doesn't it?
It does.
So instead of having separate families of particles and forces, everything is ultimately connected.
That's the beauty of grand unification.
Yeah.
It paints a much simpler and more elegant picture of the universe.
Right.
And this unification isn't just a nice idea. It has some pretty profound consequences.
Like what?
Well, for one,
Yeah.
it leads to some pretty wild predictions,
Okay.
such as the existence of new particles called X and Y bosons
Okay.
that can mediate interactions that violate some of the fundamental conservation laws we take for granted.
Violating conservation laws, like breaking the rules of the universe.
In a way, yes. These X and Y bosons can cause processes that wouldn't be allowed in the standard model alone,
Oh.
like the decay of protons.
Wait, protons can decay? I thought they were stable.
Yeah, it's a prediction of grand unification.
What would happen if the protons in our body started to decay?
That's a natural concern.
Yeah.
But don't worry, even if proton decay is possible,
Okay.
it's an incredibly rare process.
Yes.
The lifetime of a proton is predicted to be many, many times longer than the age of the universe.
Okay, that's reassuring.
Good.
But still, the idea that something as fundamental as a proton could decay is pretty mind-blowing.
It is.
Yeah.
And it highlights the potential of grand unification theories to make truly profound predictions about the nature of reality.
This is all so fascinating.
It is.
So we have supersymmetry suggesting a hidden world of superpartners.
Right.
And grand unification hinting at a single unified force governing everything.
Yeah.
Where do we go from here?
Well, the next logical step is to look for experimental evidence.
Okay.
Have we actually seen any of these superpartners?
Hey,
Have we detected any signs of proton decay?
I'm on the edge of my seat. What do the experiments tell us?
That's a great question, and one that leads us into the next chapter of our deep dive.
Okay.
We'll explore the incredible efforts to find evidence for these theories and what the results, or lack thereof, tell us about the universe we inhabit. Welcome back. We left off talking about the experimental hunt for evidence of supersymmetry and grand unification.
Right.
It's one thing to have beautiful theories, but the real test is whether they match up with what we observe in the universe.
Exactly. So where do we even begin to look for evidence of something like supersymmetry?
Yeah.
It's not like we can just stumble upon a superpartner in our backyard, right?
Not quite. The energies required to create these superpartners are far beyond what we experience in everyday life.
Right.
That's where particle accelerators like the Large Hadron Collider,
Well,
or LHC, come into play.
the LHC, I've heard so much about it.
Yeah,
It's the world's most powerful particle accelerator, right?
that's right. It's a gigantic underground ring where protons are smashed together at nearly the speed of light.
Okay.
These collisions create a burst of energy.
Mhm.
And if the theories are correct, some of that energy could transform into those elusive superpartners.
So it's like a cosmic demolition derby, smashing things together to see what new and exotic particles might emerge from the wreckage.
That's a great analogy. But there's a catch. Even if we manage to create these superpartners,
Yeah.
they're predicted to be very unstable.
Right.
They would decay almost immediately into lighter particles,
Okay.
making them incredibly difficult to detect directly.
So how do we know if we've actually created them? What kind of traces would they leave behind?
One of the key signatures physicists look for is something called missing energy.
Missing energy. How can energy go missing? Isn't energy supposed to be conserved?
You're right, energy is always conserved.
Yeah.
But in particle collisions, some of the energy can be carried away by particles that interact very weakly with the detector.
So it's like a ghost that passes through the detector unseen,
Yeah.
but we know is there because something is missing.
Exactly. That's why physicists look for a discrepancy in the energy and momentum balance of the particles they can detect
Okay.
if something doesn't add up.
Yeah.
It could be a sign that an invisible particle,
Okay.
like the lightest supersymmetric particle,
Right.
or LSP, has escaped.
The LSP. That rings a bell. Didn't we talk about that earlier?
We did.
Okay.
In many SUSY models, the LSP is stable
Okay.
and interacts very weakly with ordinary matter.
So it's like a stealthy ninja slipping through the detector unnoticed.
Yeah,
And you're saying this LSP could be the missing piece of the puzzle,
it could.
the mysterious dark matter that makes up a large part of the universe.
That's a very exciting possibility. Finding evidence for the LSP at the LHC could solve two mysteries at once: supersymmetry and dark matter.
Okay, I'm really starting to see the implications here.
Yeah,
So what have the searches at the LHC revealed so far?
right.
Have we found any evidence for SUSY particles, missing energy, or this elusive LSP?
That's the million-dollar question. Physicists have been searching for SUSY at the LHC for years.
Yeah.
But so far, no conclusive evidence has been found.
Oh, that's a bit of a letdown.
Yeah,
Does that mean supersymmetry is wrong?
not necessarily.
Okay.
The LHC experiments have set limits on the masses of SUSY particles.
Okay.
In other words,
Yeah.
they've ruled out certain mass ranges,
Okay.
but the superpartners could still exist,
Yeah.
just at higher masses than we can currently probe.
So it's like we're playing a cosmic game of hide and seek,
That's right.
and the superpartners are really good at hiding.
That's a great way to put it.
Okay.
The search continues, but the Null results have definitely sparked a lot of discussion and debate within the physics community. Some physicists are starting to question whether the simplest and most elegant versions of supersymmetry might be ruled out.
That makes sense.
Yeah.
If the superpartners were light enough to be produced at the LHC, we probably would have seen some hints by now.
Right.
But if they're heavier, we might need even more powerful accelerators to find them.
That's one possibility.
Okay.
But it's also possible that supersymmetry is realized in a more complex or subtle way than we initially thought.
So what are some of the alternative scenarios that physicists are considering?
Right.
You mentioned some frameworks like split SUSY and R parity violation.
Oh,
Can you
yeah.
explain those a bit more?
Of course. Split SUSY is an attempt to reconcile the lack of SUSY discoveries with the theoretical appeal of the idea.
Okay.
It proposes that some superpartners,
Yeah.
particularly those associated with scalar fields,
Yeah.
are much heavier than the other superpartners.
So it's like saying that some superpartners are playing hide and seek on a cosmic scale,
That's right.
while others are relatively close by.
Exactly.
Okay.
This could explain why we haven't seen the heavier superpartners yet.
Right.
But the key is that split SUSY still retains many of the attractive features of supersymmetry,
Okay.
like gauge coupling unification and the potential for a dark matter candidate.
I see. So it's a way to keep the good parts of SUSY while accounting for the lack of direct observations.
Right.
What about R parity violation? That one sounded a bit more radical.
It is. Our parity violation relaxes one of the fundamental assumptions of traditional SUSY models.
Right. R parity was that rule that ensured the LSP was stable,
Exactly.
making it a good candidate for dark matter.
Exactly.
Okay.
But if our parity is violated,
Yeah.
The LSP can decay into standard model particles,
Right.
meaning it wouldn't be a stable dark matter candidate.
So no more missing energy signature?
Not necessarily. It depends on how the LSP decays and what particles it decays into.
Right.
But it certainly makes the experimental searches more challenging
Yeah.
because we have to look for a wider range of possible signatures.
More possibilities, more complexity?
That's right.
It sounds like physicists have their work cut out for them.
They do. But that's the exciting part of scientific exploration.
Right.
We're constantly pushing the boundaries of what we know, refining our theories, and developing new experimental techniques to test them.
This has been incredibly enlightening. It's fascinating to see how the interplay between theory and experiment drives scientific progress. But I'm also wondering about the bigger picture here.
Yeah.
What are the broader implications of finding or not finding evidence for supersymmetry?
All right.
What would it mean for our understanding of the universe?
That's a profound question and one that's worth pondering.
Yeah?
The implications are indeed far-reaching, touching on everything from the nature of dark matter to the very foundations of physics itself.
Okay.
And that's what we'll delve into in the final part of our deep dive.
We're back for the final part of our deep dive into supersymmetry and grand unification. We've explored the theoretical motivations, the mathematical framework, and the ongoing experimental searches. Now, I'm really curious to discuss the broader implications. What would it mean for our understanding of the universe if we did find evidence for supersymmetry?
That's a great question. And the implications are indeed profound. If we found solid evidence for supersymmetry, it would be a revolutionary discovery, confirming a deep and elegant symmetry in the laws of nature. It would tell us that the universe is far more intricate and interconnected than we currently understand.
So it would be more than just adding a few new particles to our list. It would fundamentally change our view of the universe.
Absolutely. It would be a paradigm shift, forcing us to rethink our understanding of the fundamental building blocks of matter and the forces that govern them.
And what about some of those big mysteries we talked about earlier, like the hierarchy problem and dark matter? Would SUSY provide solutions to those puzzles?
It has the potential to, yes. As we discussed, supersymmetry offers a natural solution to the hierarchy problem by stabilizing the Higgs boson mass. And the LSP, the lightest supersymmetric particle, could very well be the elusive dark matter particle that has been evading detection for decades.
That would be incredible. Imagine solving two of the biggest mysteries in physics with one elegant theory.
It almost sounds too good to be true.
It does, doesn't it? But that's the beauty of science. Sometimes the most elegant solutions turn out to be the correct ones.
Okay, but let's play devil's advocate for a moment. What if, despite our best efforts, we continue to find no evidence for supersymmetry at the LHC or future colliders? What would that mean for physics? That's a question that has been weighing heavily on the minds of many physicists. If supersymmetry is not found, it would certainly be a challenge to our current theoretical understanding, but it wouldn't mean the end of the road for particle physics.
So it would be more of a detour than a dead end.
Exactly. It would force us to reevaluate our assumptions, explore alternative theoretical frameworks, and perhaps consider radical new ideas.
What kind of alternative frameworks are out there? Are there any that seem particularly promising?
There are many ideas being explored, and it's difficult to say which, if any, will ultimately prove to be correct. But some of the alternative frameworks that are being considered include extra dimensions, composite Higgs models, and even modifications to our understanding of gravity.
So even if supersymmetry is not the answer, the search itself will have pushed us to think more creatively and expansively about the nature of the universe.
Absolutely. The history of science is full of examples of theories that, while ultimately not correct, paved the way for new discoveries and deeper understanding. The pursuit of supersymmetry has already led to incredible advancements in theoretical and experimental physics, and those advancements will continue to shape the field regardless of the outcome of the search.
That's a great perspective. It's not just about finding the right answer, but about the journey of discovery itself.
Precisely. And it's important to remember that the universe is under no obligation to conform to our expectations or preferences. It might be that the true nature of reality is far stranger and more wondrous than anything we've imagined.
Well said. This deep dive has definitely left me with more questions than answers, but in a good way. It sparked a sense of wonder and a desire to learn more.
That's the best we can hope for. Curiosity is the driving force of science, and as long as we keep asking questions and exploring new ideas, we're bound to uncover more secrets of the universe.
Thank you so much for guiding us through this complex and fascinating topic. I feel like I've learned a tremendous amount.
It's been my pleasure. The pursuit of knowledge is a collaborative effort, and I'm always happy to share what I've learned with others.
And to you listening, we hope this deep dive has provided you with a glimpse into the exciting world of particle physics and the profound questions that drive this field.
Indeed. Whether or not supersymmetry turns out to be a part of our universe, the quest to understand the fundamental nature of reality is one of the most profound and awe-inspiring endeavors humankind has ever undertaken.
Thank you for joining us on the deep dive. Until next time, keep those minds curious.